In this lecture, I am going to present what is kinematically indeterminate structure and what is kinematic indeterminacy, and how to determine the kinematic indeterminacy of a rigid jointed frame. Then I would like to determine the kinematic indeterminacy of two problems which is based on rigid jointed plane frame. First, coming to the what is kinematically indeterminate structure. When a structure is loaded, the joints undergo displacements in the form of translations and rotations. These joint displacements are treated as unknown quantities. A skeletal structure is said to be kinematically indeterminate if the displacement components of its joint cannot be determined by compatibility equations alone. In order to evaluate the displacement components at the joints of the structures, it is necessary to consider the equations of static equilibrium. In the case of kinematically indeterminate structure, the number of unknown displacement components is greater than the number of compatibility equations. Then what is kinematic indeterminacy? The number of additional equations necessary for the determination of all the independent displacement components is known as the degree of kinematic indeterminacy or the degree of freedom. Then what is rigid jointed frame? So in the case of rigid jointed frame, the members are connected at the joint by rigid connection. There are two types of rigid jointed frame. One is rigid jointed plane frame, another one is rigid jointed space frame. In rigid jointed plane frame, at each joint there are three independent displacement components, two linear displacements and one rotational displacement takes place. Whereas in the case of rigid jointed space frame, at each joint there are six independent displacement components, three linear displacement and three rotational displacement takes place. Then how to determine the degree of kinematic indeterminacy of a rigid jointed plane frame? As we know, at each joint of rigid jointed plane frame there are three independent displacement components. So the degree of kinematic indeterminacy can be determined by taking the expression 3j minus e. So here the three independent displacement takes place in the case of rigid jointed plane frame, and j is the number of joints, and minus e is the compatibility equations. So dk is equal to 3j minus e, where 3 is the number of independent displacement takes place at each joint, and j is the number of joints, and e is the compatibility equations. Similarly, in the case of rigid jointed space frame, the degree of kinematic indeterminacy is equal to dk is equal to 6j minus e. Here the 6 indicate the number of independent displacement components in the case of rigid jointed space frame at each joint, and j is the number of joints, and e is the number of compatibility equations. So dk is equal to 6j minus e. The number of equation of compatibility is equal to the number of constraints imposed by the support conditions. As each independent external reaction component provides a constraint against the linear movement in its own direction, so the number of equation of compatibility is equal to the number of independent external reaction components. Then the equation becomes, for rigid jointed plane frame, the degree of kinematic indeterminacy is equal to dk is equal to 3j minus r, because E is equal to the number of compatibility equation, that is equal to the number of external reaction components, that is equal to the number of compatibility equations. The number of equation of compatibility, that is equal to the number of constraint imposed by the support condition, that is equal to the number of independent external reaction components, that is E is equal to R. So here the degree of kinematic indeterminacy of a rigid jointed plane frame is equal to dk is equal to 3j minus r. Similarly, the degree of kinematic indeterminacy of a rigid jointed space frame is equal to dk is equal to 6j minus r, where j is the number of joints and r is the number of independent external reaction components. Then coming to how to determine the degree of kinematic indeterminacy of a rigid jointed frame with inextensibility of the members. First, coming to the degree of kinematic indeterminacy of rigid jointed on braced plane frame with inextensibility of the members. So the formula dk is equal to 3j minus r plus m, where m is the number of members, r is the number of reaction components, and j is the number of joints. Similarly, the degree of kinematic indeterminacy of rigid jointed space frame, that can be determined by dk is equal to 6j minus r plus m. In the case of inextensibility of the members, you have to take the number of members in addition to the external reaction components. Then coming to the first problem, determine the degree of kinematic indeterminacy of a rigid jointed plane frame of a double-storied building. So this is double-storied building, 3 base double-storied building, A, B, C, D, E, F, G, H, I, J, K, L. This is the frame. So here you have to find out the degree of kinematic indeterminacy of this frame. So here the support I is fixed, L is fixed, and J is roller support, and K is hinge support. So as you know, in fixed support there are 3 reaction components, and at the roller support there is 1 reaction component, and at the hinge support there are 2 reaction components. So total number of reaction components are equal to 3 plus 1 plus 2 plus 3. Total 9. The total number of reaction components are equal to 9. The total number of reaction components, that is equal to 9, is equal to the number of compatibility equation. E is equal to R is equal to 3 into 2 plus 2 plus 1 is equal to 9. Similarly, count the number of joints. So here the number of joints are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of joints are 12. Number of joints are 12. J is equal to 12. Here each external reaction components impose a constraint on the structure, because the displacement component in the direction of a reaction component is 0. Therefore, the number of compatibility equation due to the constraint at support is equal to the number of external reaction components. Already I have explained this one. E is equal to R, that is equal to 9. Then you can find out the degree of kinematic indeterminacy. Dk is equal to 3j minus R. 3 into 12 minus 9 is equal to 27. So here the degree of kinematic indeterminacy is equal to 27. So you can give the 27 independent displacement components. So here you have to give, because at each joint there are 3 independent displacement components, 2 linear and 1 rotational. So here 2 linear, 1 horizontal displacement, 1 vertical displacement, and 1 rotational displacement. Similarly here 3 displacement, 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 and here 3 displacement. But at the roller support, there is only the horizontal displacement and rotational displacement takes place, and at the hinge support there is only rotational displacement takes place, because here the horizontal reaction and vertical reaction, so this is constant against the vertical displacement and the horizontal displacement. At the roller support, so there is constant against the vertical displacement, but the displacement takes place in the horizontal direction, and also the rotational displacement takes place. But at the fixed support, so there is constant against the 2 linear displacement and 1 rotational displacement. No displacement takes place at the fixed support. So here how many? So 27. So 3 plus 3 plus 3 plus 3, 12 numbers. 3 plus 3 plus 3 plus 3, 12 numbers. So total 24 numbers from this. And here 2 displacement takes place, 26, and here 1 rotational displacement takes place, 27. So the total 20. This is the independent displacement takes place on the structure. So this is the direction of the 27 independent displacement is given in this figure. So these are the independent displacement components: 3, 3, 3, 3, 3, 3, 3, 3, and here 2 and here 1. So these are the 27 independent displacement components. Then how to determine the degree of kinematic indeterminacy for inextensibility of the members. In the analysis of a rigid jointed frame, it is commonly assumed that the members are inextensible. Generally, in the rigid jointed frame, it is commonly assumed the members are inextensible. This assumption regarding inextensibility of members imposes additional constraint on the displacement of the support. In figure 3, it is evident that due to inextensibility of the column, joints A, B, C, D, E, F, G, H cannot have any vertical displacement. These constraint provides 8 number of compatibility equations. Here, so at joint A, joint B, joint C, joint D, joint E, joint F, joint G, and joint H. So there are no vertical displacement in the case of inextensibility of the members. So due to inextensibility of the column, joint A, B, C, D, E, F, G, H cannot have any vertical displacement. So these constraints provide 8 compatibility equations. So these constraints, because there is no vertical displacement at joint A, B, C, D, E, F, G, H, so these 8 constraint provides 8 compatibility equations. Then the inextensibility of the beam provides 6 equations of compatibility. Here you see, so this is the beam, this is beam, this is beam. So here, what is the displacement takes place at A? The same displacement takes place at B, C, and D. Similarly, what is the displacement takes place at E? The same displacement takes place at F, G, and H. So here, so this the constraint of horizontal displacement provide the 6 number of compatibility equations. The horizontal displacement of joint B, C, T are the same as that of joint A, so provide 3 compatibility equations. Similarly, the horizontal displacement of joint F, G, H are the same as that of joint E and provide 3 compatibility equations. What is the horizontal displacement takes place at B, C, D? That is equal to the horizontal displacement of A. Similarly, what is the horizontal displacement takes place at F, G, H? That is equal to the horizontal displacement of E. So here provide the 6 compatibility equations. So from this 3 compatibility equation and from this 3 compatibility equation. Hence, the inextensibility of the members provide 8 plus 6, total 14 compatibility equations. From the column, from the joint, there is no vertical displacement takes place, and that provide 8 compatibility equation, and from the inextensibility of the beams, that provide 6 compatibility equation. So the inextensibility of the members provide 14 number of compatibility equations. The number of constraints or the number of compatibility equations due to inextensibility of the member is equal to the number of members. So here you have to see the number of compatibility equation due to inextensibility of the member, that is equal to the number of members. From the inextensibility of the members, here you got 14 compatibility equation. So that is equal to the number of members. So here you count the number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the number of members, that is equal to the number of compatibility equation due to inextensibility of the members, that is equal to m is equal to 14. Then you can find out also the degree of kinematic indeterminacy of this frame due to the inextensibility of the members by using this formula also: dk is equal to 3j minus r plus m. So here j is the number of joints, r is the number of external reaction components, and m is the number of members. So here dk is equal to 3 into 12 minus 9 plus 14, that is equal to 13. So the degree of kinematic indeterminacy of rigid jointed plane frame, that is equal to 13 due to the inextensibility of the members. Then the direction of the displacement are given in this figure. At the joint A, there is no vertical displacement, horizontal and rotational displacement takes place. At joint B, there is no vertical and there is no horizontal, because what is the horizontal displacement takes place at A, the same displacement takes place at B also. So here no need to take any horizontal displacement. So here only rotational displacement takes place at B, and at C rotational displacement takes place, at D rotational displacement takes place, and at E there is a horizontal displacement and rotational displacement, and at F rotational displacement, at G rotational displacement, and at H rotational displacement, and at J roller support there is a horizontal displacement and there is also the rotational displacement, and at K due to hinge support there is only the rotational displacement takes place. So these are the independent displacement components due to the inextensibility of the members. Then coming to the second problem, determine the degree of kinematic indeterminacy of a rigid jointed plane frame of a three-storied building. So this is three-storied building, three-storied and three-base building. So here A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And here the support M is fixed, support P is fixed, support N is roller support, and support O is hinge support. So at the fixed support, so there are 3 reaction components, and at roller support there is 1 reaction component. At the hinge support, so there are 2 reaction components. So the total number of reaction components are equal to 3 plus 1 plus 2 plus 3, that is equal to 9. So this reaction components, that is equal to the number of compatibility equations. So the number of compatibility equation due to constraint at support is equal to the number of external reaction components, that is equal to E is equal to R is equal to 3 into 2 plus 1, this is equal to 9. You have to count how many joints are here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The number of joints are 16. J is equal to 16. Then you can find out what is the degree of kinematic indeterminacy. So the degree of kinematic indeterminacy for rigid jointed plane frame you can find out by using this expression: dk is equal to 3j minus r, and here you know j is equal to 16 and r is equal to 9. So 3 into 16 minus 9, so this is equal to 39. So this is the degree of kinematic indeterminacy of this rigid jointed plane frame of three-storied building. As you got the degree of kinematic indeterminacy are equal to 39, so you have to give the 39 independent displacement components. So at A there are 3 displacement takes place: the horizontal displacement, vertical displacement and the rotational displacement. Similarly at B 3 displacement takes place: C 3 displacement, D 3 displacement, E 3 displacement, F 3 displacement, G 3 displacement, H 3 displacements, I 3 displacements, J 3 displacements, K 3 displacements and L 3 displacements. But at N there is only the horizontal displacement and the rotational displacement takes place. There is no vertical displacement due to the vertical reaction is the constant against the vertical displacement. And at the hinge support there is no vertical displacement and there is no horizontal displacement due to the constant, that is the vertical direction and the horizontal direction against the vertical and horizontal displacement. Only the rotational displacement takes place. And at M and P there is no displacement takes place. There is no horizontal displacement, there is no vertical displacement and there is no rotational displacement. So the total number of displacement takes place, that is equal to 39. So this displacement is given in this figure. The direction of the 39 independent displacement components, that is delta 1 to delta 39, is given in this figure. 3 displacement, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3 and here 2 and here 1. So this is the total independent displacement components of this three-storied frame. So this is when the members are extensibility takes place. Here you have to find out the degree of kinematic indeterminacy due to the inextensibility of the members. So due to the inextensibility of the members, so here you see in figure 3, it is evident that due to inextensibility of the column, joints A, B, C, D, E, F, G, H, I, J, K, L cannot have any vertical displacement. So this constraint provides 12 compatibility equations. Here you see at joint A, B, C, D, E, F, G, H, I, J, K, L there is no vertical displacement takes place due to inextensibility of the members. So this constraint provides 12 number of compatibility equations. These are the beams. So what is the displacement takes place at A? The same displacement takes place at B, C, D. Similarly, what is the displacement takes place at E? The same displacement takes place at F, G, H. And what is the displacement takes place at I? The same displacement takes place at J, K, L. So here you have to take one displacement for this beam. For this story beam, you have to take one displacement. Instead of 4 displacement, you have to take only one displacement. Here also, instead of 4 displacement, you have to take only one displacement. Here also, instead of 4 displacement, you have to take only one displacement, because the displacement is same at all the joints in the horizontal direction. So here the horizontal displacement of joint B, C, D are the same as that of joint A. So this provides 3 compatibility equations. Similarly, the horizontal displacement of joint F, G, H are the same as that of joint E. So this also provides 3 compatibility equations. Then the horizontal displacement of joint J, K, L are the same as the joint I. So this also provides 3 compatibility equations. So the total number of compatibility equations from the beam constraint, that is equal to 9. 9 equations of compatibility provide the inextensibility of the beams. Then what is the total number of compatibility equations due to inextensibility of the members? So due to column there are 12 compatibility equations, and due to beam there are 9 compatibility equations. Then the total number of compatibility equations due to inextensibility of the members is equal to 12 plus 9, that is equal to 21. The number of constraint or the number of compatibility equations due to inextensibility of the members is equal to the number of members. So here you have to see, so this is the 21 compatibility equation you got from the inextensibility of the members. So this is equal to the number of members. So here you count the number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 21. So here you got 21, the number of members are equal to 21, and here the number of compatibility equation due to inextensibility of the members also you got 21. So you can find out the degree of kinematic indeterminacy by taking the inextensibility of the members. So the degree of kinematic indeterminacy dk is equal to 3j minus r plus m. So here you know j and r and m. M is the number of members, r is the number of external direction components, j is the number of joints. Then after putting the value of j, r, m, so you can find out what is the degree of kinematic indeterminacy. dk is equal to 3 into 16 minus 9 plus 21. So this is equal to 18. Here you got the degree of kinematic indeterminacy, that is equal to 18 due to inextensibility of the members. Then you can give the independent displacement components at each joint, because here at the joint A there are horizontal displacement and rotational displacement takes place, but at joint B there is no vertical displacement and there is no horizontal displacement, only the rotational displacement takes place. And at joint C also rotational displacement, joint T rotational displacement, joint E horizontal displacement and rotational displacement takes place, and joint F rotational displacement, joint G rotational displacement, joint H rotational displacement, and joint I horizontal and rotational displacement, joint J rotational displacement, joint K rotational, and joint L rotational displacement. And at support N there is horizontal displacement and rotational displacement, and at support O there is only rotational displacement takes place. So the total number of independent displacement components are equal to 18. And the degree of kinematic indeterminacy of this frame is also equal to 18. So accordingly, so this is the independent displacement component directions. Now all are clear what is kinematically indeterminate structure and what is kinematic indeterminacy, how to determine the kinematic indeterminacy of rigid jointed plane frame with extensibility of the members and without extensibility of the members.